Hello everyone and welcome back to the channel! Today I'm taking you along on an exciting journey, my very first attempt at implementing a specific two-axis motion using microcontrollers. Our goal for this project is simple in theory, but packed with engineering challenges. We want to achieve perfectly smooth and precise movement along a specific 2D path. To do this, we are using two NEMA 17 stepper motors, two AS5600 magnetic encoders, two A4988 drivers, and a cool dual microcontroller architecture. One controller is dedicated solely to reading encoder data for precise feedback, while the other acts as our mastermind, sending the exact pulse commands to the drivers. But to start moving, we need a path. The trajectory I've chosen is a B-spline curve, shaped like the Greek letter omega, which I mapped out in the Design Mentor software. But how do we translate this path into mathematical language for our system? The answer is parametric curves. In classical math, we usually use equations like y equals f of x, but in motion control, that method is too restrictive. In a parametric curve, like the B-spline I'm drawing right now, both the x and y coordinates are functions of an independent variable, called the parameter u. Mathematically, we express this as p of u, which gives us the exact coordinates for both x of u and y of u. This parameter u typically goes from 0 at the start of the path to 1 at the end. This powerful method allows us to easily model highly complex, continuous curves without ever worrying about infinite slopes along the way. Before touching the hardware, we headed over to MATLAB to simulate our motion algorithm. Let's look closely at the graphs to see why choosing the right motion profile is absolutely critical. First, the trapezoidal velocity profile, or constant acceleration. If you look at its velocity graph, it ramps up in a straight line. But the problem happens right when the acceleration jumps from 0 to its maximum. Mathematically, this sudden step-like change means the derivative of acceleration, which we call jerk, spikes to infinity. The physical result on our machine? Sudden impacts, severe mechanical vibration, and heavy wear and tear on the stepper motors. Second, we have the trigonometric jerk profile. As you can see on the graph, the changes in acceleration are completely smooth and curved. No more infinite jerk. However, this method has two massive flaws for our project. Because trigonometric functions are naturally slow at the start and end, this algorithm is not time optimal, extending our total travel time significantly. Also, calculating continuous sine waves creates a very heavy processing load for a simple microcontroller. And finally, our winning algorithm, the jerk-limited or S-curve profile. Notice how the velocity graph looks like a stretched letter S? In this method, we limit the rate of acceleration change. The jerk is no longer infinite, it is safely capped. This algorithm strikes the perfect balance. It makes the stepper motors run incredibly smooth and completely vibration-free. But because it uses linear polynomial equations, it's much faster, and our microcontroller can easily handle the math in real time. Now, it's time to bring these simulations to the hardware. We wrote our code in the Arduino IDE, but here is the crucial detail. This algorithm must run in strict real-time. The output of this algorithm is the interpolated value of the curve parameter u for every single time cycle. In motion planning, this is called parametric curve interpolation. Every single millisecond, our algorithm calculates exactly what u should be. As our flowchart shows, we plug that parameter u into the B-spline equation to get the exact x and y coordinates. Finally, these calculations generate the exact electrical pulses for the A4988 drivers, timed perfectly by the jerk-limited profile to guarantee a smooth acceleration. And here is the final result. As you can see and beautifully hear from the motors, the system follows the omega path with the smoothest possible acceleration. The live data you see drawing on the monitor perfectly matches the real-time algorithm, turning our curve parameters into physical movement. This